Hello everyone, Typhoon here again, and today we begin one of the most fundamental and powerful journeys into low-level programming, understanding x86 64 assembly, or understanding the registers in x86 64 assembly. So if you want to know how CPU thinks, how it manipulates data, executes instructions, and controls memory, then you must understand the registers. Now this lecture is long, dense, and packed with everything from beginner insights into detailed breakdowns meant for feature reverse engineers and low-level programmers. So you may ask here, what are the registers? At the lowest level of computing, a register is tiny, lightning-fast piece of memory inside the CPU itself. Registers temporarily store data that's being actively used or manipulated by the CPU. They are fundamental to every operation your processor performs. Now you can think of the registers as the working hands of the CPU. So instead of grabbing data from random access memory or RAM every time, which is much slower compared to the CPU first grabs it into a register, manipulates it, and then sends the results back to the random access memory, RAM, if needed. In x86 assembly, there are multiple types of registers, each grounded based on function or grouped based on function. The first, we have GPAs. This is not universal GPA here, this is general purpose registers. This perform like arithmetics, logic, and memory access. And we also have the segment registers, which manage segmented memory addressing. We have the flags register, which tracks the results and CPU states after operations. And we also have the instruction pointers, like IP, EIP, and RIP, which basically shows where the current instruction is. Now let's dissect each category right now. First, we will start with the general purpose registers. General purpose registers. So the original x86 architecture began with 36-bit GPRs, general purpose registers. These include, the first is accumulator, AX. Let's actually change the color, write it in a different color, AX. So this is accumulator, used heavily for arithmetic, multiplication, and system calls. We have base register, BX, often stores base addresses in memory operations. We have CX, control register, commonly used in loop operations such as rep move SP. Let's actually also write the abbreviation for this as well. We have DX, which is data register, often used alongside AX in division multiplication, also for input-output port addresses. We have the source index and destination index. Now these used in string operations and array traversal. We have stack pointer, points to the top of the stack, and we have the base pointer, helps access function parameters and local variables within the stack. Let's also write the abbreviation so you can see it as we explain. Now here we are. Now this register can also be split into 8-bit halves. Now for example, in the AX we have the AH, which is the high byte, and AL, which is the low byte. And for example, in BX we have the BH, which is the high byte, low byte. Not byte, sorry, it was bit. So remember, so 8 bits, 16 bits. And yeah, same applies for the other registers as well. CX to CH, 16-bit, CL, 8-bit, DL for 8, DH for 16-bit again, and DL for 8 bits, since L here means low. And same goes on like this as well. Now that means you can manipulate single bytes efficiently, which is extremely useful for low-level data handling. And when x86 architecture was extended into a 32-bit, also called the IA32, now these registers became the EAX, which is EAX, like EBX for the base register, ECX for the counter register, EDX for the data register, like SI, ESI, and so on and so forth. And in the 64-bit, which is what we call it, in the 64-bit, which written is like that, x86. Let's actually use different colors so we don't. Yeah. For example, x86. Now this is 64-bit. So remember, this was the 16-bit, 32-bit here, and the 64-bit registers we have here. The most used today is 64-bit registers, but depends on the CPU architecture as well. Now they expanded to the RAX accumulator, RBX for the base register, RCX for the counter register, RDX for the data register, and added from R8 all the way to the R15, making 16 full general purpose register. Number 1, 2, 3, 4, 5, 6, 7, and from R8 1, 2, 3, 4, 5, 6, 7, and from the R8 to R15 it just 16 full general purpose register. And we all have the stack pointers as well. Now SP and BP also transition to and also get another meanings. So SP turns to ESP here, P, and EBP for the base pointer. Now this points to the top of the stack, changes automatically with the push and pop instructions. And for the 64 bits, it also changed In the 64-bit, we have the RSP and RBP here. Here, SP stack pointer turns to 32-bit ESP, and in the 64-bit we use the RSP. So RSP points to the top of the stack, changes automatically with the push and pop instructions, and RBP, ABP, BP, these are basically the base pointer as well, base pointer to reference the stack frame, which is this, we will use this in function calls. Now every register can be accessed in parts, like RAX, EX, X, like this RAX. We can use the RAX to the EX to the X here, and for the lowest we have the AL and AH, which I have explained here. Number and the bits increase and increase as from right to left in this diagram, which allows for flexible manipulation of data sites. So if you don't need the 64-bit registers, but you're computing on the 64-bit CPU, you can just use AL to save from computing power, which you will learn that more deeply in next lectures. Now let's also explain the instruction pointers in the next lecture. This was the part 1 of the first lecture. This is, as I said from the starting of this lecture, these are very important for learning assembly languages. It doesn't matter if it's in an ARM or another assembly language. If you know the base understanding of this, how assembly works, you can apply the same principles on ARM or other MASM or other assembly languages here. So thank you for watching. I'm Typhoon, and I'm waiting you in next lecture.